In the previous video, I hope I successfully convinced you that it's worth looking at the tangent line at a point, that is to say the line tangent to the graph of a function at a point. So here I have a function's graph, f of x. There's my a, there's a comma f of a. F of a would be the y-coordinate here. And the tangent line would look something like that. All right, it's the best linear approximation, worth remembering. Best linear approximation to our function f of x at the point a comma f of a. Right, and if f of x represents the distance and the x-axis represents time, so that's distance, then the slope of this line is the instantaneous velocity. So it's the velocity that you're traveling at that instant in time. So here it looks like it would be some very large negative value. So for that value of t equals a, that would mean that you're running backwards pretty darn fast. Okay, so then the question became, how do we actually find the equation of this line? And I reminded you guys that, you know what, there is such a thing as the point-slope formula for finding the equation of a line. If you know what one of the points on it and you know what the slope is, then you have your point-slope formula. You can use it, plug it in, and directly find the issue. So we already know a point that the line passes through, obviously, this point that comes for free, a comma f of a. So that takes care of the point, but what about the slope? That's the real issue. And I didn't talk at all about how you would actually go about finding the slope. So I want to show you how you would do it in this video. Alright, so first of all, we'll address how to actually do it in theory, because the most efficient way of actually computing it is going to be a little bit more complicated, but in order to understand the formulas, we're going to have to start with the following kind of idea. So the idea here is you take this line, and this line is characterized because it kind of just passes through that one point on the function. It might pass through some other points near, later on, but nearby it just kind of passes through that one point. So that's what makes it a tangent line. If you hear the word tangent, usually it means that it just passes through one point. So things are a little bit complicated in this context, but the thing you want to consider is a secant line. Secant means that it passes through 2 points on the graph. So you would pick some other point on the graph and you would draw the line that connects those two. And then you would move that point along the graph closer and closer to the point that you're interested in. And as you can tell, the closer you move it, the more these lines, these secant lines, approximate our tangent line. So I've drawn some secant lines here. So what we have here is a certain point right there on the graph, and we have the line between our point of interest, a comma f of a, and this point. If this is our b, then this would be the point b comma f of b, of course, because it lies on the graph. So we'd be looking at the slope of the line, or the line passing between a comma f of a and b comma f of b. Now again, as far as the tangent line, let's not lose sight of our goal here. We're interested in finding the equation of the tangent line. We don't care so much about the secant lines. They're not terribly good approximations, but the tangent line is a really good approximation. But in order to find the equation of the tangent line, we need a point it passes through, and the slope. We already have a point it passes through. All we need is the slope. So the reason we're considering these secant lines is because the idea is if we know what the slope of each of these secant lines is, then we can somehow use that to figure out what the slope of the tangent line ought to be. Because they kind of converge, each of these lines. As we pick closer and closer values of b, the b is approaching a on the x-axis, then hopefully these secant lines passing through a comma f of a and b comma f of b will get, those slopes will in the limit converge to the slope of the tangent line. So what is the slope here? What's the slope of this line? Well, okay, it's just rise over run, right? So let's draw it out. Alright, so there's our rise, and of course it's just the change in y. That's f of a minus f of b, or f of b minus f of a, however you want to write it. It doesn't matter. And this one is b minus a. That's your run. Right? So, of course, I mean, this is f of b minus f of a divided by b minus a is your change in y over change in x, and that is your slope of the secant line. Alright, so like we said, we're going to take this b, this point here, and we're going to move it along the graph here. So the actual x value b here is moving closer and closer to a as we go. We're picking b's that are nearing a. So what we want to do is we want to take the limit as b approaches a of this quantity, f of b minus f of a over b minus a. So it's worth remembering that just one of these guys represents the slope of the secant line. Remember, secant line is the line passing through the point of interest and some other point on the graph going through b comma f of b. So if we take the limit as b approaches a, then hopefully these slopes will, in the limit, approach the slope of our tangent line. You can kind of see how the blue lines kind of converge to this green line. So that's the quantity that we're actually interested in. There's another way that you might see it written. They might say, you know what, b, so let me switch colors here. Let's switch over to red. Any given one of these b's, let me just pick this b, is really just a plus some quantity h. So there's nothing fancy going on here. We're just saying, you know, let's write b in the form a plus h. H is just that distance between a and b. Okay, so this isn't really a fancy thing or complicated. Obviously, for any number, you just let h equal b minus a, and you can find a number that you add to a to get to b. This is just a change in notation. We're not doing anything fancy. I have no tricks up my sleeve. But if we write it like that, then this b minus a here can be replaced with an h. And this f of b, well, if b is a plus h, we would write it like that, and we're subtracting f of a as before. So we would have f of a plus h minus f of a. And the limit as b goes to a, you know, b is getting really, really, really close to a, is really saying the same thing as this error between h, this error h between b and a is getting smaller and smaller. Obviously, as h gets closer and closer to 0, b is going to get closer and closer to a. So instead of writing the limit as b goes to a, we could write the limit as h goes to 0. So you might also see this formula. Both of these formulas represent the slope of the tangent line. So they both represent the slope of the tangent line, tangent to the graph, and passing through the point a comma f of a, which is what we were looking for in the first place. Okay, so there's usually a favorite notation for this thing, and I'll talk more about this notation in a later video, but sometimes it'll be called f prime of a. So right now that's just a notation. You don't have to worry too much about it. But it's this limit by definition, so this is the actual definition of it, or this is an equivalent definition of it. They mean the same thing. And it just represents the slope of the tangent line. It literally is that value. And as we said before, you know, not every function has that. So for example, a function with a little corner, you can't actually pull this off. And I also want to make one more remark here. As I've been drawing these secant lines, I've always been picking b to the right of a. So I've always been assuming that h is kind of a positive number here. But there's really no reason I would have done that. I'm just too lazy to have drawn. Really what you should have done is you should have also picked b's over here on this side and looked at the corresponding value and drew the secant line for those, and you would have had lines coming in from the left as well as the right, and all the rest. So this isn't supposed to be some kind of one-sided limit coming from the right. No, it's a two-sided run-of-the-mill limit, and we want to let B approach A from either side, and look at secant lines coming from each of those sides. So this is in theory how you would actually go about computing, or at least defining, what the slope of this tangent line is. So what we should do in later videos is we'll combine this information. So now how do we figure out? So we're going to use the point slope formula. So how do we find the equation of the tangent line? So here's my formula for the slope. And I'll leave that for another video. I think I could write down the formula right now, but I think it's already pretty abstract, and I'd like to get an actual function in place before I show you how to do that sort of thing. But for the remainder of this video, I just want to give you an example of what we've just done. So let me give you a simple function here. Let's consider the function. I don't know, that's not a very good drawing, but let's consider the function x squared plus 2. So that's what the graph would look like. It's a parabola, but it's been shifted up by 2. And let's pick the point x equal to 1. And then what would that point be? Well, if you plug 1 into this, you'd get 1 squared plus 2. That would be a 3. So that's the point 1, 3. And I'm interested in finding the tangent line there. I want to know what is the slope of the tangent line at 1, 3, tangent to the graph of f of x equal to x squared plus 2. Alright, so what you would do is you would go and you would write, so here my a is equal to 1, right? A is the x coordinate of the point we're interested in. So my a is equal to 1, and my f of a is equal to 3. Let me write it out. A should be 1 in this context. F of a should equal 3 in this context. And so really the function of b that I'm interested in is f of b minus f of a, but f of a is 3, over b minus a, but a is 1. So I'm interested in this function, or if I expand what f actually is, x squared plus 2, that's really equal to b squared plus 2 minus 3 over b minus 1. Or just the 2 and 3 combined, that's b squared minus 1 over b minus 1. And that actually simplifies, doesn't it? As long as b is not equal to 1, this can be broken up into b minus 1 times b plus 1. We have a b minus 1 on bottom, so those will cancel, and we'll get b plus 1. But remember that this isn't defined, is not defined for b equal to 1. So that even though this simplified version is defined, because the original formula isn't defined, we still have to draw a hole in our graph. So what does the graph of this look like? Well, it looks pretty much like the graph of b plus 1, where now b is the variable. It's not the x-axis anymore, it's the b-axis. And it's shifted up by 1. Except for at the point that we're actually interested in, right? So what we would do is this is the quotient, f of b minus f of a over b minus a, but then what we're really interested in doing is taking the limit as b approaches 1, as b approaches a, and remember a is 1. But that's exactly where we have a hole in our graph. So this is one of those situations, and this is really the reason we've been considering these types of situations. This is one of those situations where the limit exists, but the function value itself doesn't exist. So in the language of the previous video, the limit as x approaches a, I'm using b right now for other reasons, but in that video I called it x. The limit as x approaches a of f of x exists, even though f of a doesn't. And I should really be careful with this language here. This is not the same f. This is not the same s. I should have called it a different name, like g or something like this. Because the function that I have drawn here, this is the graph of the function. Well, I already wrote that function down, didn't I? This function. f of b minus 3 over b minus 1. So it's related to f, but it's not equal to f. It's something that's built up out of f. Okay, so we'll actually see more examples of this, and we'll see how we can combine this with passing through a point and the point slope formula to actually write down the equation of a tangent line, something you might be able to do right now as an exercise already.